In the last lesson, we introduced the basic proof rules for natural deduction and looked at a few example proofs. In this lesson video, we're going to cover a general strategy for approaching these natural deduction proofs. And the strategy I'm going to describe is going to be a little different than the one described in the text, but still the fundamental rules for constructing formal proofs in this system are going to be the same. So the point of this lesson video will be to introduce to you and illustrate a strategy for constructing proofs in this natural deduction system we've been covering. So you're always required to start your proof by listing any assumptions that you have for the proof. And in cases where you're proving validity, that will be your premises. In a few lessons, we'll actually look, though, at some example proofs where you don't start with any assumptions, but are still able to prove the conclusion. Once you've got your assumptions listed, your main goal should be to identify the main connective in each one of those starting assumptions. The purpose of doing so is that the main connective tells you what elimination rule you could use to apply to each of those assumptions. So if the main connective in one of your assumptions is a biconditional, that tells you that if you want to access either of the sentences that compose the biconditional, you're going to have to use biconditional elimination. Once you know what the main connective in each of those starting assumptions is, your goal should be to apply any non-subproof elimination rules to your assumptions. For example, if you have a conjunction, you should apply conjunction elimination right away. The point of doing so is that it makes available sentences that you might be able to use later in your proof. So you infer everything you can from your starting premises that you can do without starting a subproof. Then, whatever sentences you have before your subproofs will be available in the main body of your proof, and so available for the entire rest of your proof. Once you've done everything you can with non-subproof rules, look to your conclusion to guide your next steps. So instead of thinking, what additional rules can I apply to the premises? Instead, look to your conclusion. Identify the main connective in your conclusion. That will tell you what rule you'll most likely apply first in your steps along the way to proving that conclusion. Then, use rules that allow you to introduce the connectives in the conclusion. So if the main connective of your conclusion is a biconditional, you're going to have to use the biconditional introduction subproofs, starting pretty early on in your proof. The goal of doing this is that it allows you to build up the conclusion from the lines of your proof. Remember when we talked about what the sentences of truth functional logic are, we showed that every sentence can be built up from atomic sentences and connectives. Your proof will similarly build up sentences piece by piece in general. With that in mind, you should aim to add smaller subsentences of your conclusion to your proof on earlier lines than more complex subsentences of your conclusion. So if your conclusion contains D, and that's a part of D or G, you should add D to your proof before G. And while you're considering rules that you have to use to introduce the connectives in your conclusion, if those rules require subproofs, you want to start the subproofs for wider scope connectives in your conclusion before the ones that introduce your narrower scope connectives. So the narrower scope connective proofs will be part of the subproofs for wider scope connectives. Those are some very general statements of how the strategy works. So let's look at a couple of examples in which we'll use elements of this strategy. Here we're asked using the basic rules of natural deduction to show that the following argument of truth functional logic is valid. The premises are if D and E, then not F, F or G and W, if D, then E. And from those, we're supposed to be able to conclude if D, then G. So our proof has to start out, in this case, with the premises as our assumptions. And those take up our first 3 lines. And then to the right there, I've just noted our conclusion again for reference. So we've got the slash to separate it from our justifications. And then the 3 dots for therefore to symbolize that that's our conclusion. If D, then G. This isn't necessary, but it's a nice reminder when the proof gets long. Now let's put our strategy in place. Our strategy tells us to start by looking at the main connectives of our premises. So for the first assumption, it's this conditional. For the second, it's a disjunction. And for the third, it's a conditional. And now we're supposed to ask ourselves, according to this strategy, are there any non-subproof rules that can be applied at this stage? Well, definitely not to the second one. Because it's a disjunction, the only rule we could apply is disjunction elimination. But that's a subproof rule. So that isn't exactly where you'd want to start. 1 and 3 are conditionals, and the conditional elimination rule is a non-subproof rule. So if we could apply that now, we should. The problem is that to apply conditional elimination, we have to have both the conditional on one line and its antecedent on another line, and we don't have a line that contains the antecedent of either of these conditionals. So it turns out for this proof, there is no non-subproof rule we can apply right off the bat. That means we need to look to our conclusion and think about how to work from these premises to our conclusion. So this is the thinking backwards portion of the proof strategy. We need to identify the main connective in our conclusion. Well, there's only one, so that makes it a little simpler. It's this conditional. If we're going to get a conditional at the end of our proof, we need a rule for introducing a conditional. So we need the conditional introduction rule. That's a subproof rule. So that's what we should start with now. This conditional introduction rule tells us to assume the antecedent, and we justify assuming the antecedent with assumption for conditional introduction. It's always good to remind yourself what your intention is when you start a conditional proof. And your goal several lines down at some point should be to get G at the end of this. Because if you get G at the end of this subproof, you can add if D, then G to the end of your proof, and it's done. Remember too that not only do we have to add the assumption for our subproof, we also have to add the line that marks that this is a subproof within the body of the main proof. And we have to mark that D is the assumption and everything else that follows is proved within that subproof. Now, once we know that D is true, we can actually apply some of our non-subproof rules. So again, it's generally best to do that as soon as possible when you can. So once we have D, we look at line 3, that's the antecedent to that conditional. So that means we can apply conditional elimination and get E. So that's conditional elimination on lines 3 and 4. Are there any other non-subproof rules we might be able to use? Well, the only other thing we could apply a non-subproof rule to is if we used another conditional elimination. And to do that, we would need D and E. Well, we can get D and E. Once you have both conjuncts in your tree, you can add a conjunction. So that's our conjunction introduction rule from lines 4 and 5. And that allows us to conclude not F. So that follows from conditional elimination from lines 1 and 6. At this point, we've used our premises 1 and 3, but we haven't used 2 yet. The only rule, though, that we have to get into those sentences that make up 2 and use the parts of 2 is with disjunction elimination. The other thing that suggests we're wanting to break up 2 is that 2 contains the sentence G. That's the sentence we're looking to prove. So that's another reason to think that by working with 2, we might get to our conclusion. Because disjunction elimination requires 2 separate subproofs, each of which starts by assuming one of the disjuncts, you may find it helpful to remind yourself to do both subproofs by starting both of them with an assumption that you need and then leaving several lines to complete the subproof. And that may be 2 or 3 lines or maybe 10 lines. Leave yourself some space. So this one is going to start by assuming F, and then I need to mark that that's the start of a subproof and that's my assumption, and justify it as an assumption for disjunction elimination. Then I can go down a few lines. We don't know what numbered line this is going to be yet, but it needs to start by assuming the other disjunct, which is G and W. And that'll be another assumption for disjunction elimination. And again, we mark that that's our assumption. So now we can work with the first one for a minute. Note right away that by assuming F, we have its negation at line 7. Once we have a sentence and a negation accessible to it, we can add a contradiction. So that follows by our rule negation elimination from lines 7 and 8. We also know that if we prove a contradiction, we can prove anything at all. That's what our explosion rule tells us. So if we were to apply the explosion rule, given line 9, what sentence would be useful to infer at this point? Well, if we're going to get if D then G as our conclusion, it seems like it would be really useful to be able to infer G. We also need it to be a sentence that we can prove from this other subproof too. And since this contains G as one of its conjuncts, we'll be able to prove G from that other one too. So that's the sentence we should add using explosion. That completes that proof. And then now we can move on to our second subproof. We just need to move that one up. So G and W allows us to conclude G because conjunction elimination allows us to add one of the conjuncts. Now, what does disjunction elimination tell us? If you can prove the same sentence from both disjuncts, in this case we've proved G, you can add that outside of your subproofs. So we can add it outside of these two to the subproof that we started at line 4. Note that you can only close one subproof at a time, or one pair of subproofs at a time, by applying one of our rules. So that's why I always suggest naming the assumption, because this tells you can only use these two subproofs to add a sentence that follows from this rule. And you can only end this subproof by adding a sentence that follows from this rule. So for this one, we get G by disjunction elimination by two subproofs. One is from lines 8 to 10, and the other is from lines 11 to 12. Since our disjunction elimination allowed us to conclude G, that was the consequent we were looking for all along. So now we can add if D, then G to our tree. That follows from conditional introduction, and we cite this whole subproof, lines 4 to 13, and we're done. We've completed our proof using the strategy we had in mind. Let's apply this strategy now to a second example, also asking us to use our basic proof rules to show that an argument of truth functional logic is valid. This one has two premises and a conclusion with multiple connectives. So we have if A or B, then C, if C or D, then F, and from that we can conclude if A, then E or F. Like the previous example, we have conditionals in our assumptions, but we can't eliminate these conditionals because we don't also have assumptions of the antecedents of these conditionals. So there are no non-subproof rules we can apply right away. That means we need to look at our conclusion. Our conclusion contains two connectives. We need to figure out which one is the main one, because if that requires a subproof, that's what we need to start with now. So our conclusion is if A, then E or F. The main connective is that conditional. That tells us we should start with a conditional introduction at line 3. What should we assume? We should assume the antecedent. And we mark with our vertical line that we're starting a subproof, as usual. There's nothing more we can do with just A on its own, so we need to look at our assumptions and our conclusion as a guide for where to go from here. Let's start by looking at our conclusion. We need to get E or F as the conclusion of this subproof that started with the assumption of A. How do we introduce a disjunction? Well, we can introduce a disjunction as long as we have one of the disjuncts in the proof. So we need to either prove E or F. If we look at our premises, we'll see that line 2 contains F. So at some point, that's going to lead us hopefully to prove F, and we can add E or F to the tree from that. But we can't use line 2 unless we can get the antecedent, C or D. Since line 1 contains C, we're probably going to have to work with that first. And we have a rule that allows us to get the antecedent. The antecedent is a disjunction, and the disjunctional introduction rule allows us to add any disjunct once we have one of the disjuncts. So we have A, and we could add any second disjunct. In this case, it's useful to add B, because that will give us the antecedent to that conditional. So that's disjunction introduction applied to line 3. And now we can get C by conditional elimination applied to line 1. And it turns out the structure of 2 is the same. We can apply that same reasoning again. We have C or D, so we can add C or D because we have one of the disjuncts because of disjunction introduction. So that's applied to line 5. And now we have the antecedent of our other conditional, so we can infer F. I'm going to go back and add. I see that I made a mistake here. That's lines 1 and 4. Need to justify it with both lines, and I need to make sure I do that here too. So conditional elimination applied to lines 2 and 6. And now that we have F, as I said before, and as we've done already twice, we can infer a disjunction. You can add the disjuncts in either direction, so you can add E or F. That's by disjunction introduction applied to line 7. Now we have the antecedent of our conditional at line 3, and by assuming that, we've proved the consequent. So we may add the conditional to our tree. And that is what we wanted to conclude all along. That follows from conditional introduction, lines 3 to 8. And there's our proof. Now that you have a general strategy to work from and illustrations of how to implement it, aim to practice as many proofs as you can. They get easier the more you become comfortable with the strategy, and also as you just get familiar with approaches that help you when you feel a little bit stuck.